Today's topic, integrals involving trigonometric functions, is a pretty broad topic, but I think I can show you some pretty good methods to solve a good portion of these. So if you have something like sine to the n cosine to the m of x, an integral in that form, there is kind of a method to solve that type of a problem, where n and m are non-negative integers. So if n and m are both even, we're in the first type of a case where you do it in a certain way. So I'll jump right into a problem like that. Sine squared of x. Now there doesn't seem to be a cosine to a power of x, but remember that everything to the 0 power is 1. So we can think of this as sine squared of x cosine to the 0 power of x. So both are even, n and m. So in this case, what you do is come back to these trigonometric identities that you learned back when you took trigonometry, maybe in pre-calculus class. These are not just busy work. We could not do this integral without these trigonometric identities. So on this one, we're going to replace sine squared of x with what you once proved that it is. 1 minus the cosine of 2x all over 2. And it makes life easier because we went from a second power to just a first power. So if we just split this up now, we can take the 1/2 out front, and we just have 1 minus the cosine of 2x dx. And we can take both of those integrals. The antiderivative of 1 dx is x, minus the antiderivative of the cosine is the sine, but since it's 2x, I have to divide by 2. And then you add your general constant, and you've got an answer. So that's the only way to do that integral, and that's not that unusual of an integral. So it's nice that we really have that technique. Same thing here. 2, 2. N and m are both even. So I'm going to use both of these identities. For sine squared, I go 1 minus the cosine of 2x over 2. And for cosine squared, 1 plus the cosine of 2x over 2. And because you have 1 minus and 1 plus, conjugates, besides being able to take the 1/4 out front, when I multiply these together, I just get 1 times 1 minus cosine squared of 2x. Now, it didn't work out quite as nicely as this one because I've got cosine squared. But again, cosine squared just puts us into the same thing where we have to use our identities. So 1 minus, and what am I going to put in place of cosine squared of 2x? I'm going to use this, but I put a 2 there, which means I have to put a 2 there, and it becomes 1 plus the cosine of 4x over 2. So I get 1 plus the cosine of 4x all over 2, and this whole thing dx. So probably what you want to do is combine things together. 1 minus 1/2 is 1/2, and then you have minus the cosine of 4x all over 2. Now I think we can take these antiderivatives. The antiderivative of 1/2 dx is 1/2 x. And the antiderivative of the cosine is the sine, but then we have to divide by 4, and it's already divided by 2, so then it's going to be over 8. plus c, and we've got an answer. Okay, so much for case 1, when they're both even. This time, 2 is even, but 1 is odd. When you have a case like this, what you have to do is pull one of the odd ones out to become your du. Well, since this is only to the first power, it's already kind of pulled out. So I'm just going to leave it there, and this is going to become du. Well, the derivative of the cosine is minus the sine. So this is almost in the form of du. But I still need a little minus sign. And I can put that in there as long as I also multiply by -1 out front. Negative times a negative brings you right back to where you were. Now, what I have there in parentheses, if I think of u to be the cosine of x, du is minus sine of x dx. So I've got it in the form of u squared du. So the antiderivative is just u cubed over 3 plus c. You got an answer. Now, if you're still not quite feeling comfortable with doing that, you can go through and change this back into u squared du and take the antiderivative and then put it back in as the cosine of x. But I think if you get used to this, doing the u substitutions without actually writing them out, you're going to find that you like it. Okay, here's another one. Cosine cubed of x, sine to the 0 of x. So one of them is odd. That one you have to pull out. So cosine squared of x, now I'm going to multiply it times cosine of x. This has to become my du. Well, the trouble is, cosine is not the derivative of cosine. It's the derivative of sine. So we want everything on this side really to be in terms of sine. Well, that's where we go to this other identity, that Pythagorean identity. Sine squared plus cosine squared is 1, so cosine squared is 1 minus sine squared. So now you can rewrite that into two integrals. We have the cosine of x, and then we have minus the integral of sine squared of x, cosine of x, dx. Well, the antiderivative of the cosine is the sine, and look at, this is perfect. If I think of u to be the sine of x, du is the cosine of x dx. So it's exactly in the form of u squared du. I don't have to do any adjustments. So I just get u cubed over 3 plus c. I'm done. So lastly, in the sine to the n, cosine to the m, I've got one where both of these are odd. Well, that's still case 2. Only one of them has to be, but if both of them are odd, then you have your choice. Which one do I want to pull out? Do I want to pull out a sine, or do I want to pull out a cosine? It's really going to make a difference. So I'm going to show you what I'm going to do, and then I'll show you later why I picked that one. I'm going to pull out a sine. So make it sine squared of x times sine of x dx. This is going to become my du. Well, it's going to become the du to the cosine. So I want everything over here to be in terms of cosine. Well, cosine to the 17th x is, but sine squared isn't. But using that same Pythagorean identity, sine squared is 1 minus the cosine squared of x. And if I rewrite this into two integrals, I get cosine to the 17th times sine and then minus the integral of cosine to the 19th. We're almost there. If we think of u to be the cosine, the derivative would be minus the sine. So again, I need a minus sign right here. So I'm going to put a minus sign out front, and the same thing on this side. So now it's in the form of u to the 17th du. So the antiderivative is u to the 18th divided by 18. And this one is in the form of u to the 19th du. So the antiderivative is u to the 20th over 20 plus c. So that kind of ends all the sine to the n, cosine to the m. So I'm just going to give two more examples of different type of trigonometric integrals. And I didn't pick anything particular for this one because there isn't any special technique to solve it. So what we have to do is kind of use our knowledge of what we've learned in the past. Like, what are the relationships that are important? Well, we kind of know that the derivative of the tangent is the secant squared. And if we think back to our trigonometry, we know there's some relationship between tangent and secant. Sort of like there's the relationship between sine and cosine. There's another Pythagorean identity. And I always forget what it is. I just know it exists. So I go back to this one and I divide everything by cosine squared of x. And I should be able to do that. Divide both sides by the same thing. Sine squared divided by cosine squared is tangent squared. This is just 1. And 1 over the cosine squared is the secant squared. So this is the other Pythagorean identity. So what I'm going to do is come down here. I don't want to get rid of all the tangents. I want to get tangent and secant together. So I'm going to call this tangent squared of x, and then make the other tangent squared of x secant squared minus 1. And I've done what I hoped to do. I got tangent along with secant squared. That's a nice matchup. So if I rewrite this tangent squared of x, secant squared of x, by distributing this through, minus the integral of tangent squared of x. Now I'm going to wait on that one. Let's just go back to here. Is this one in a nice form? Yes. If I think of u to be the tangent of x, this is u squared, and that's exactly du. So this part just becomes u cubed over 3. Now I've got to put in this distribution tangent squared. But I don't know the antiderivative of tangent squared, and I do of secant squared. So instead of tangent squared here, I'm going to put secant squared of x minus 1. And now look what I've got. Minus the integral of secant squared, which is minus the tangent of x. And then minus times minus is plus the antiderivative of 1 dx, which is x, plus our general constant. And we've solved one that we really had no technique or knowledge of how we were going to go about doing it, but we just used our relationships, and it worked. Now, I'm going to end this one up with an integral that you'll probably never have to do one quite that hard on a test. But it's such a cool integral. There's maybe not a cooler integral out there. So I think everybody should see this done once in their life, at least. So, you look at secant cubed and think, what can I do? And my thinking is maybe integration by parts. So, what are the two parts going to be? I'm going to think of this as secant squared times secant. And what's a really good thing to put for dv? Secant squared of x. Because the antiderivative of secant squared is tangent. For u, then I have to put the secant of x. And then du is secant of x, tangent of x, dx. So I've got it all set up. What does integration by parts say? The integral right up here, which I might as well write that down, what I'm finding is equal to u times v, the secant of x, tangent of x, minus the integral of v du. So I get secant of x times tangent squared of x. Instead of tangent squared, I'm going to write secant squared minus 1. Then I get secant x tangent x minus, if I distribute this through, I get the integral of secant cubed of x, and then minus times minus is plus the integral of secant of x. Look at it. This is what I started with, and I've got it here. Am I going in circles? I've seen this happen once before. No, this is minus. So I can take all of this and move it to the other side of the equal sign and combine it with this, and then we have 2 equals secant of x tangent of x. This is now gone. I just have plus the integral of secant of x dx. But I don't know what to do with secant of x dx. So what I'm going to do is multiply by 1. But I'm going to pick the form of 1 that I want to use. And what it is secant of x plus tangent of x over secant of x plus tangent of x. I just multiplied by 1, but in kind of an unusual way. And you're probably thinking, why in the world did I do that? Look at the mess I've got. But look what happens if you multiply out the numerator. Secant times secant is secant squared of x, and secant times tangent is secant of x tangent of x. So if you cross that out and put this in the numerator, look what you've got. The derivative of tangent is secant squared, and the derivative of secant is secant tangent. So it's exactly in the form of du over u. So this is just the natural log of the absolute value of secant of x plus tangent of x. And then this has always just been here. And the only thing you have to do to get one of these is to divide by both sides by 2. You add your constant, and we have an answer for what the integral of secant cubed of x dx is. So, kind of not any kind of technique. We just saw that maybe integration by parts would work. This was probably the most obscure thing, but look how cool it worked out when you got that into the form of du over u. So I hope you enjoyed that one. This just gives you an idea how to attack integrals that have trigonometric functions in them. So take care.